Okay, so hello everyone. Thank you for being here. So today we have a new Cosmos seminar. So I'm very happy to introduce you to Javier Huenupi. For those of you who haven't heard from Javier, he did his undergrad here at the University of Chile, and now he's a master's student under the guidance of Gonzalo. Right? Just to tell you a little bit about Javier, his academic interests are primordial cosmology and quantum field theory. And today he is going to present about regularizing infrared divergences in the Cedar spacetime. So thank you, Javier, for being here, and please take it away whenever you're ready.
Okay, thank you, Gal. Hi, everyone. First of all, thanks for being here. It's for me an honor to be here at home, and not, for example, at Universidad Católica, like previously. So it's not important. Today, I'm going to talk about one of my thesis projects titled Regularizing Infrared Divergences in the Cedar Spacetime. And it's obviously important to mention that this work has been done in collaboration with Eli Hughes, the Spiro Sipsas, both of them are present here today, and my master's degree advisor, Gonzalo Palma, that now he is in Korea, I think. North Korea? South Korea. Okay. It's the same. Well, so let's start this talk. So first of all, let's talk about some of the motivation to do this project. So all of us know that if we are interested in explore that the primordial physics at high energy levels, we can use one of these giants particle accelerator, for example, the Large Hadron Collider, the LHC, that is from CERN, and it is placed in the frontier between France and Switzerland. And in this collider, depending on the experiment, we know that we can produce collision of the order of 10 tera electron volt. That is a good number, but it's nothing compared to the energy of the early universe. That is around 10 to the 13 tera electron volts. I mean, that is 13 orders of magnitude greater than the most energetic process that we can produce here on our terrestrial particle collider. So, thus, cosmic inflation provides us of the biggest particle accelerator of the universe. And due to the energetic environment and the gravitational field trend, we have that in this period where a lot of collision, a lot of interaction between particles, and that interaction left their marks on our observable universe. And what is the greatest cosmological observable that we have? Well, the cosmic microwave background, the CMB. So we need to work the theory and compute possible observables to be able to search for these quantum marks that left there, the dust interaction. So when we talk about work the theory and compute possible observables, we are talking about compute mathematically information about those fields. For example, as we are talking about quantum fields, we can compute their probability density function, the PDF. That for a free theory, we know that we will get a perfect Gaussian distribution for a quantum field called, for example, phi. But we know that if we consider interaction, for example, self-interaction or interaction between other fields, for example, in a multi-field inflation model, we know that we would get an almost Gaussian distribution. That is a Gaussian distribution with some structure. You can see that in that paper. So we are interested on these PDFs. So how can we compute them? Well, we need to compute endpoint correlation function. That is basically the expectation value of the quantum field that we are interested on. In this case, we call it, for example, phi. And we need that this expectation value is evaluated, or I mean, every field phi is evaluated at the same time and a final time, for example, T sub F. For example, the time where the cosmic microwave was created. And we have that these fields are evaluated at different spatial points, in our case, the CMB. So to do the computation of this expectation value, this endpoint correlation function, we know that we need a specific theory. In our case, we need a specific Lagrangian. So in this project, we use the most basic Lagrangian density that we can imagine, where the first term is the cinematic term, the second one is the mass term, and the last one is the potential, considering only self-interaction of our quantum field phi. We can consider an interaction between other fields, for example, in a multi-field inflation model. But now in this work, we are considering only a single field inflation model. And to raise and lower indices, we have a background metric that is a de Sitters metric with the function A, that is the scale factor of our spacetime, that is in function only on the time and is operated only over the spatial part of the metric. But watching this Lagrangian, what about the potential B? What is the potential B? So this is an important topic of this talk, so let's talk deeply about it. So as we remember from our first courses of classical mechanics, we know that we can plot the potential of our theory and plot the mechanical energy too, so to interpret the behavior on the movement of the particle in different situations. So we will do something similar. But first, I don't know if somebody knows in this room, but I have no idea of what is the specific potential that follows this primordial field. So we will consider an arbitrary potential represented by this green light, but we require only one thing over this potential. It needs to be much less than h to the 4, where h is the cosmological constant, and obviously is a constant. And we require it because we want to be able to do perturbative computation of the Feynman diagram that we will see later. So we need only this, nothing more. But we need to do mathematical computation, we need a specific expression and an explicit expression of this potential phi, of this potential B, sorry. So our first try could be, for example, approximate this potential B as a quadratic function, where we have this coupling constant, lambda sub 2. But it could be great. For example, let's think about this red ball as if it was our quantum field. So we have this red ball that it will be oscillating around the phi equals to 0. So if we have a small perturbation around phi equals to 0, we have that the potential is well approximated by our approximation, the orange line. But as we are dealing with quantum fluctuation, with quantum fields, we know that the particle can tunnel across the potential and gets a new minimum. Where now the approximation, the quadratic approximation, is not a good approximation of our potential in that position. So we need to consider more terms to our approximation. In this case, we have now this new orange line that is an approximation until up to 5th order. So where now, again, we have a good approximation of the field where the ball is located. But again, we know that the particle or the field can tunnel across the potential again and again and again and gets more to the right or more to the left infinitely. So finally, we conclude that we need to consider every polynomial term to the expansion of the potential B. And it is Basically, the Taylor expansion of the potential, considering the m equals to 0 to infinity. So now we have that doesn't matter where the ball is located. We have the potential is well described by our approximation, that in this case is the expansion, the Taylor expansion. So now we need to have a mathematical procedure to do the computation of these expectation fields. So we will use the Feynman diagrams in a cosmological constant. In specific, we will use the Schwinger-Keldysh path integral formalism that you can review it in that link. So Feynman diagrams and correlation function are very related between them, because if we want to compute endpoint correlation function, we need to draw Feynman diagrams with an external legs. So we're interested in this object, that is the expectation value of the field phi, where now the files are evaluated on the momentum k1, k2, kn, because now we are working in momentum space. So to draw the Feynman diagrams, first we need to draw an horizontal line that is evaluated at a specific final time. In our case, for example, where the CMB was created. So, and also we need to draw this white square labeled with the momentum k1, k2, kn, that is the external momenta of our theory. And depending on our specific theory, we will have different interaction or different rules that give us the number of legs that could come from a single vertex. So remember that in our case, we are considering the full Taylor expansion of our potential B. So, but we will not talk too deeply in this. So we only need to know that we need to attach the external legs that come from this white square, and we have that the external momenta enter to the diagram from this white square. But due to we are considering the potential needs to be much less than h to the 4, we can consider the leading contribution, that is considering Feynman diagrams with only one vertex. That is represented with this circle with a crossing side, and represent every diagram that has only one vertex. We will see what I'm talking about. So we can have one of our diagrams that we need to consider is the tree-level contribution. It's the diagram that has the n external leg and has a single vertex, because we are considering, remember, only diagrams with one vertex. So, but now this is a very easy diagram. We can compute it. It's not too complicated, but we can consider these objects that we call daisy loops, that are internal legs that come from the single vertex of the diagram and closes on itself. And in these daisy loops, we will have an internal momentum, call it K, for example, that will be flowing inside only this daisy loop. And it's important to mention that this internal momentum is independent of the external momentum. And due to we are considering the full expansion of the potential, the full Taylor expansion, we can consider an arbitrary number of those daisy loops. So remember that we want to compute this diagram where we call that this dot with a cross represent the complete vertex. So we need the first contribution to the Feynman diagrams with only a single vertex is the tree-level contribution, that is this one, that has no loops. And the next one will be a tree-level diagram, remember, is this, but considering only one daisy loop. And next to it, we can consider a diagram with 2 daisy loops, with 3 daisy loops, 4 daisy loops, and so on and so forth. But this is a problem because following the Feynman rules of our theory or our formalism, we know that we need to integrate the internal momenta of these daisy loops from k equals to 0 to k equals to infinity. So we will get infinite contribution coming from these daisy loops. But this is a problem because the left-hand side of this equation, this diagram from here, needs to be a finite quantity. So if it is a finite quantity, but we have the right-hand side that is full of infinities, so we have a problem. And we need to solve it developing a mathematical procedure to erase these infinities. And now let's talk about this mathematical procedure, call it renormalization, that is the art of erasing infinities. So, as we saw, the Feynman diagrams are full of infinities, so we conclude that the parameters of our theory, in our case, when I talk about parameters, I'm talking about the coupling constant lambda sub m of the Taylor expansion, actually are bare parameter. So let's focus only on this coupling constant. So we need to split this coupling constant into two contributions. The renormalized coupling, that is a finite quantity, and a content coupling, that could be an infinite number. So now we will do explicit the bar dependence of the coupling constant, putting a b in the superindex. And also, as you saw, we can consider an arbitrary number of daisy loops. So we also need to expand the content coupling into different contribution, where we do explicit the loop order dependence of each coupling constant, where, for example, lambda super 1 represents a coupling constant of order 1 loop. Lambda super 2 is a coupling constant with an order 2 loop. Lambda sub 3, 3 order on loop. So you can think about it, for example, when you try to solve the anharmonic oscillator, where we have this nonlinear differential equation. And we know that our first try would be expand the position of the mass into different contributions, considering different orders of our theory. But we know that if we replace this expansion, this type of ansatz, we will get that the position of the mass gets an infinite value at a certain time. So it cannot be possible. We know that the spring has a finite length. So we also need to consider an expansion of the frequency of the oscillation. So we can think that this expansion of the frequency of the oscillation is the same as the expansion that we are considering on our quantum field theory. So now let's see the case of diagrams with one loop. The first diagram that we are going to deal is this. That is a diagram that itself has only one daisy loop. So we say that the diagram itself is ordered one loop. So following the Feynman rules of our formalism, we know that we need to multiply this Feynman diagram with its coupling constant. In this case, it's the renormalized coupling, this lambda sub n plus 2. This n plus 2 is because we have n external legs and 2 internal legs that form the daisy loop. So, and following the notation of the contour term, we know that this renormalized coupling is a coupling that is order 0 on loops. So, as we need to multiply these two terms, with the multiplication of these two terms gives us a full contribution that is order 1 loop. So, and we know that the integral coming from the daisy loop is an infinite quantity. So we need to sum up another diagram that needs to be the same order, in this case, order 1 loop, but considering a contour coupling. So the only possibility that we have is considering the following diagram. That is a tree-level diagram. So the diagram itself is ordered 0 in loops, but it's multiplied by a coupling constant, a contour coupling constant, that is ordered 1 loop. So the multiplication of these two terms give us a full contribution that is 1 order on loop. So we sum these two terms, and as I said, and we need that the sum needs to be equals to 0 to kill completely the infinite coming from the daisy loop of the diagram of the left. So, but as you can see, we have the both diagrams have the same external legs. So we can factorize them and we can worry about only on the different parts of each diagram. So we will have this diagrammatic equation, but we need to translate it into a mathematical equation to do computation. So following the Feynman rules, we will get this expression where this 1/2 is a symmetry factor that comes from flip the daisy loops, and the integral inside of the square brackets is the contribution coming from the daisy loop. That is an integral over the internal momentum and the propagator that represent this internal line. So as we see, this internal momentum k is a dummy variable, it's an integration variable. So the full integral is an infinite, but also is a constant. So let us call it only just like C. Okay. So now we have this equation, and it's easy to get the expression of the contour coupling lambda super 1. That is the expression here, where we see that in the right side we have the renormalized coupling. That is a finite quantity, but see, is an infinite. So lambda super 1 is an infinite too. We can allow that. So now let's see the case of two loops, where we have that the diagram of the left, the diagram itself is ordered 2 loop because it has 2 daisy loop, and the coupling constant is ordered 0 in loop. So the multiplication of both of the two terms give us a contribution of order 2 on loops. So we need to sum up every diagram possible that it also order 2 on loops. So we have this two contribution, where the diagram itself is ordered 1 loop because it has 1 loop, and the constant term is ordered 1 loop. So the multiplication of these two terms give us a full contribution of order 2 loop. And it's the same here. We have that the diagram has no loop, so it's 0 ordered on loop, but the contour term is ordered 2 loop. So the multiplication is ordered 2 on loops. So summing up these two terms, we get that it needs to be equal to 0 to kill completely the infinite coming from the daisy loop of the diagram of the left. So now the mathematical equation coming from this diagrammatic equation is this, where we have this new symmetry factor, this 1/2 factorial, that comes from flip different daisy loops. And also we have the same 1/2 that comes from flip the same loops once. And now, using the previous result for lambda super 1, we can get easily that the contour term lambda super 2 is equal to this expression in function of the renormalized coupling. And we can do this again with 3 loops, 4 loops, 5 loops. So we can prove by induction that for the L contour term, we need the following expression. What is the expression here? So considering this expression for the contour term coupling, now we have that the complete vertex is now a finite quantity. That is what we want. So let's recall that we are doing this computation where in the left-hand side we have the complete vertex and every possible diagram with only one vertex. So let us put the coupling constant of each diagram, that we have this. And also, the same as before, we have that each diagram have the same external legs, so we can factorize them, and we can worry about only on the different part of each diagram. So we have this diagrammatic equation, but recall that we split this pair coupling constant into a renormalized coupling, that's a finite quantity, and the content term coupling that is also expanding in different orders. So now we will have a copy of each of these diagrams, where one copy will be multiplied by a renormalized coupling, the first line, and the second line we will have diagrams multiplied by content term diagram. So using the expression of the content term that I showed you, finally, we will get that the sum of these diagrams is equal to 0. So now we have this equation where these dots and this circle with a cross has a value of 1. So we finally get this, where now, as the renormalized coupling is a finite quantity, now we have that the observable coupling is also a finite quantity. But there is several regularization methods, but now let's talk about of the dimensional regularization that allows us to subtract only the loop divergent part. So until now, we have been working on a 3+1 dimensional de Sitter spacetime. But when we do dimensional regularization, we go to now a 3 plus delta plus 1 dimensional de Sitter spacetime. And after doing the necessary changes in, for example, the mode function, the coupling constant, finally, we can get an expression of the coupling of the loop contribution. Let's remember that we call that the basic loop contribution. We call it C. We can expand considering delta going to 0, and we will get this expansion here, where we know what are the values of A is where 2, space over 1 is where 2, 3, or 4, but it's not important. The important thing is that they are finite quantities. But it's important to notice that as delta goes to 0, we have that the first term is a divergent part, and the rest of the expansion is a finite quantity. So using a similar answer as I showed you before, we can consider that the content coupling can subtract only the divergent part, where now we have inside the parentheses the divergent part of the loop contribution C. And considering this content coupling, we will get a slightly different expression of the complete vertex than before it was that, but now we will have this expression. That the important thing is that inside the parentheses, we will have that the function is the finite part of the loop contribution, and taking delta equals to 0, the only thing that left is the coefficient alpha sub 2, and in our case, in our theory, we compute it, and is this green function. So, getting to the conclusion, we have that considering an arbitrary potential is not too complicated, but it needs to be at first order. And now we are able to consider an arbitrary number of daisy loop. This is important because many authors and many works, they work only with, they compute diagrams only with, for example, one daisy loop, two daisy loop. But now we are able to compute diagrams and renormalize the theory, considering diagrams with, in a single diagram, has, for example, 500 number of daisy loop, and we can do that. So is a good thing. I know, I think. And as future works, we have that we want to try to do something similar, but now considering diagrams with two vertices. We know that it will be hard because now the diagram that has two vertices inside the loops, it can be flowing external momenta, and it complicates a lot the mathematical computation. And also, I think it could be worth to explore the use of the mass scale, this mu that I showed you before, that allows us to do in a more formal way this perturbatively procedure. Okay. That is all that I wanted to talk about. So, gracias por su atención.
Okay, thank you, Javier, for your great presentation. So we have time for a couple of questions. So if anyone has one, please go ahead. And then
I'm Team Curtidos. My question is a very naive question, but I work with some formulas similar to you. But did you say you establish that the potential, the amplitude of the potential is thresholded for h to the 4? Why? Why did you put this threshold?
That is because we write the Lagrangian density. We have the cinematic term plus the mass term minus the potentials. So, but this Lagrangian is written in function of, for example, the physical space, the space position and the physical time. So, but if we consider now the matrix, because remember that we have that the action is so is this. So if we compute this determinant of the matrix and change from the physical time to conformal time, we will get that this potential needs to be written, for example, like something like that. So we need that this quantity needs to be much less than 1 to get to do perturbative mathematical computation. So
it's for extract the dependence of H4, right?
can you repeat?
Yes, it's for just extract the H4 dependence in potential with this.
No. That is because from the determinant of the matrix, we get this. And when we go from T to conformal time, now we get another scale factor contribution. So finally, we will have something like this. And
Yeah.
h to the 4, because well, h expressed function of conformal time is this.
Okay.
So now we have that this term multiplied specifically the potential. So now we need that this needs to be much less than 1. So
Yeah.
that's the requirement.
I understand. Thank you.
Thank you for your question.
right, you have a question.
You're working with sugar credits diagram,
Yes.
right? So you're computing close time, close time path intervals, right?
Mhm.
With positive forward moving. So I was wondering if you could modify your variable for canceling divergences by, because if you look at the rules, you always have a vertex for the positive fields and a vertex for the negative fields.
The blacks and the white vertex.
Yeah.
Okay.
So in the end, you will have like the real part or the imaginary part of
Yeah.
the vertex. So maybe I was wondering if you could not ask to remove all the divergence of the diagram, but maybe just keep the real part, for example. I don't know if I make
That is an interesting question, but no, but I have an answer. So it is due because, for example, how can I do that? We will get, for example, diagrams of this type, considering L number of daisy loops. We'll have that this is proportional to lambda observable sub m, because we have n external legs, and it's multiplied by, as you say, is 2 times, for example, the imaginary part of the time integral of propagators until the last thing. So we have this part, that is the imaginary part of the integral of the propagator of the external leg. But as the daisy loop contribution is time independent, we can take out this coupling constant outside the integral, and now it's multiplying the whole term. So now we see that if we're considering this daisy loop without a renormalization theory, this is an infinite. So we need to do this like a finite quantity. So we already considered the subtraction of the real part of each vertex of. So we need to do in any case. We are considering that.
Maybe you could modify the C factor maybe times, like not the interval of G, but maybe the interval of the imaginary part.
Good question. No, that is not necessary, because we have that because of the fact that a daisy loop is an internal line that comes from the single vertex and encloses on itself. It doesn't matter what vertex is the vertex of the diagram. If it is a black vertex or a white vertex, the expression is the same. Because you can see the propagators of our theory, that if we have a propagator that is evaluated an internal momentum and come from the vertex we evaluated at time t and go back to the same vertex, we'll have that. If you call it the propagator for a black vertex, it's the same as the propagator with white vertex. So it doesn't matter the type of the vertex that we are considering in the diagram is the same expression of the propagator, because of this we are evaluated at the same time, the start and the ending of the internal line.
Okay, thanks. One last question. What ensures that this is time independent? Like,
Yeah,
because I see that because of time you're integrating this vertex over all time. What makes that time independent in the scheme of renormalization?
yeah. That is basically because, as you say, the propagator itself is time independent, but we are computing the integral momentum of this propagator evaluated at k, tau, and tau. So basically, this whole expression is time dependent, because the propagator is time dependent. But if we do a change of variable, like for example, k equal to minus k multiplied by tau, we will get that the time dependence disappears. It's a change of variable. And it's great because we can take up this term that it will be here, but as in time independent, we can take off of the interval. Thank you very much for the question.
Any more questions? I do have one. So what do you expect, what are the complications that you expect when considering higher verdicts and thus different loop topologies? I mean, like you mentioned that now there is incoming momentum flow into the loop. I can also see that you now have time dependence on the bulk propagators, but do you expect any more complications besides those?
Yeah, we will have complication because if we consider diagrams with two vertices, for example, two black vertex, we'll have something like this. So if we are not now considering only daisy loop, but because we can consider daisy loop in this case, but this is the three-level contribution. Now we need to consider loops that are of this form, for example, this form. So now we will have an internal momentum, okay, for example, but now inside the loop, it would be external momentum flowing inside this loop. So the complication is more in the part when we go back from Fourier space to coordinate space, because now we have the momentum, the external momentum in different part of our expression. So it's basically a problem when we go back and coordinate the space.
Okay.
So we have mixed the external momentum in the whole expression.
Oh, right. And why do you want to go back? Because typically we don't go back, right?
Yeah.
Keep working momentum space.
Yeah, that is because one of the reasons to do this type of computation, the endpoint coordinate function, the randomization, and all of this stuff, is to compute PDF. And the formula of to compute PDF needs to be expression value evaluated at a specific space point. So we need to come back to coordinate. You are able to do that.
Sure. All right, thanks. Any more questions? If not, let's thank you.
Okay, yeah.
What's that? Puro animales,